Beneath the surface, most of Earth remains unknown. We have mapped the face of Mars in greater detail than we have charted our own ocean floor. Right now, in this very moment, there are valleys deeper than the Grand Canyon, mountain ranges taller than the Alps, and ecosystems stranger than anything we have imagined, all hidden beneath a darkness so complete that sunlight has never once reached it. And tonight, together, we will sink slowly into that quiet unknown, letting the deep carry us gently towards sleep. The ocean covers more than 70% of our planet's surface. It holds roughly 97% of all the water on Earth, and within its volume exists the largest living space in the known universe. And yet, as of the most recent estimates, we have explored and mapped in high resolution only about 5% of the global ocean floor. The rest remains as mysterious to us as the far side of a distant moon. Think of that for a moment. We live on a world defined by water, shaped by tides, governed by currents that regulate our climate, and still, what lies beneath those waves is, in almost every meaningful sense, a frontier. Tonight, we will descend together through the layers of the sea, from the sunlit shallows where light still plays across the sand, down through the twilight zones, past the midnight boundaries, and into the abyssal plains where pressure and darkness reign in a silence older than memory. Let this journey carry you. Let the weight of the water above feel not like pressure, but like a blanket, folding you gently into rest. Let us begin where the light still reaches. The uppermost layer of the ocean is called the Epipelagic zone, sometimes known as the sunlight zone, and it stretches from the surface down to roughly 200 meters, or about 650 feet. This is the ocean most of us know. It is where waves roll and break, where coral reefs pulse with color, where dolphins arc through warm currents and sea turtles glide beneath hulls of passing boats. Sunlight penetrates this layer, and because of that, photosynthesis is possible here. Phytoplankton, those microscopic plant-like organisms drifting in uncountable billions, produce roughly 50% of the oxygen we breathe. Half of every breath you take tonight was born in this thin, luminous band of water. And yet even here, even in the most accessible part of the sea, there is so much we do not fully understand. We are still discovering new species of fish in shallow tropical waters. Marine biologists estimate that hundreds of thousands of ocean species remain unnamed and undescribed. The Census of Marine Life, a decade-long international project completed in 2010, catalogued approximately 250,000 known marine species, but the researchers involved suggested the true number could be over 1 million, perhaps many more. Consider the strangeness of that. We have been sailing these waters for thousands of years, casting nets, diving with masks and tanks, deploying satellites and sonar, and still the sunlit shallows hold secrets we have not yet touched. But the sunlight zone is only the beginning. It represents less than 2% of the ocean's total volume. The real unknown begins where the light fades, where the blue deepens into indigo, and indigo gives way to black. So let us sink a little further now. Let the warmth of the surface release you, and feel the water grow cooler, heavier, quieter around you as we descend past the reach of the sun. Below 200 meters, we enter a realm known as the Mesopelagic zone, the Twilight zone. It extends downward to roughly 1,000 meters, a little over 3,200 feet, and it is here that the ocean begins to reveal its more alien character. Some light still reaches this layer, but only as a faint, scattered glow, not enough for photosynthesis, not enough to see by in any human sense. And yet life here is not scarce. It is, in fact, staggeringly abundant. Scientists estimate that the Mesopelagic zone contains more fish by mass than all other ocean layers combined, possibly 10 billion metric tons of biomass, though the true figure remains uncertain and is one of the active frontiers of marine research. Many of the creatures here have evolved bioluminescence, the ability to generate their own light through chemical reactions. It is estimated that roughly 76% of ocean creatures possess some form of bioluminescence. In the Twilight zone, this living light serves 100 purposes. Some organisms use it to attract prey. Others use it to communicate or to camouflage themselves against the faint glow of the surface above, a strategy known as counter-illumination. One of the most extraordinary residents of this zone is the bristlemouth fish, a small, unassuming creature with delicate jaws lined with tiny teeth. Despite being largely unknown to the general public, bristlemouths are thought to be the most abundant vertebrate on Earth, with population estimates reaching into the hundreds of trillions. They rise toward the surface each night to feed and then descend again before dawn, participating in what is called the Hadal vertical migration, a daily movement of organisms that is considered the largest migration of biomass on the planet. Every night, beneath every ocean, this great silent journey repeats, and no one on the surface sees it happen. Let that settle over you now, the knowledge that while you rest, the sea is in motion, quietly, endlessly, carrying its creatures through the dark. Deeper still, below 1,000 meters, the ocean enters what is known as the Bathypelagic zone, the midnight zone. It stretches from 1,000 to 4,000 meters, roughly 3,200 to 13,000 feet, and here no sunlight reaches at all. The temperature hovers near freezing, typically between 0 and 4 degrees Celsius. The pressure is immense, reaching 400 atmospheres at its deepest boundary, which means that every square inch of surface at that depth bears a weight of nearly 6,000 pounds, and yet life persists. The midnight zone is home to creatures that seem almost imagined. The giant squid, Architeuthis dux, was known for centuries only through the stories of sailors and the occasional tentacle found in the stomach of a sperm whale. It was not until 2004 that a team of Japanese researchers led by Tsunemi Kubodera and Kyoichi Mori captured the first photographs of a living giant squid in its natural habitat deep in the North Pacific. The images revealed a creature both graceful and enormous, with eyes the size of dinner plates, the largest eyes in the animal kingdom, adapted to detect the faintest traces of bioluminescent light in the surrounding blackness. Down here, food is scarce. Most nutrition arrives from above in the form of what marine scientists poetically call marine snow, a slow, continuous rain of dead organic matter, fragments of plankton, fecal pellets, shed mucus, and decaying tissue drifting downward from the productive layers above. This gentle fall of particles is the primary energy source for most deep-sea ecosystems. It can take weeks for a single flake of marine snow to descend from the surface to the abyssal floor. Imagine that. A quiet, patient rain that has been falling since the oceans first formed, nourishing the dark. In the midnight zone, patience is not a virtue. It is the fundamental law of survival. Everything here waits, And so tonight, perhaps, we can learn something from this patient darkness. There is no urgency in the deep. There is only stillness and the long, gentle fall of nourishment from above. Below 4,000 meters, we enter the Abyssopelagic zone, the abyss. The word itself comes from the Greek abyssos, meaning bottomless, and though we now know the ocean does have a floor, this name still captures something true about the feeling of this place. The abyssal zone extends from 4,000 to 6,000 meters and covers roughly 60% of the Earth's surface, making it the single largest habitat on the planet. And it is overwhelmingly flat. The abyssal plains are vast, sediment-covered expanses that stretch for thousands of kilometers with barely a ripple in their topography. These plains are blanketed in layers of fine ooze, sediment composed of the accumulated shells of countless trillions of microscopic organisms that lived and died in the waters above over millions of years. In some places, these sediment layers are hundreds of meters thick, a geological record of ocean life stretching back tens of millions of years. The pressure here exceeds 600 atmospheres. Temperatures hover between 1 and 4 degrees Celsius. And yet, even in this seemingly barren landscape, there are surprises. Polymetallic nodules, roughly fist-sized rocks rich in manganese, nickel, cobalt, and rare earth elements, lie scattered across the abyssal plains like strange dark eggs. They grow extraordinarily slowly, accreting new material at a rate of only a few millimeters per million years, making them among the slowest growing geological formations known. Some nodules on the ocean floor today began forming tens of millions of years ago. These nodules have attracted significant commercial interest, and the question of whether and how to mine them is one of the most pressing environmental debates in ocean science today. Conservation scientists worry that disturbing the abyssal floor could destroy ecosystems we have barely begun to understand, communities of organisms adapted to conditions of stability measured not in centuries, but in geological epochs. For now, the abyss keeps its treasures. The sediment lies undisturbed. The nodules continue their impossibly slow growth. And the silence of the deep floor stretches out in every direction, patient and unhurried, like the breath of someone drifting gently towards sleep. And then, beyond the abyss, there is one more realm, the Hadal zone. Named for Hades, the ancient Greek god of the underworld, this is the ocean's deepest domain. It begins at 6,000 meters and plunges downward into the ocean's trenches, those narrow curving scars in the seafloor where tectonic plates collide and one dives beneath another in a process called subduction. There are roughly 33 known Hadal trenches on Earth, and together they occupy less than 1/4% of the ocean floor. But they are the deepest places on the planet. The deepest of all is the Mariana Trench, located in the western Pacific Ocean, east of the Mariana Islands. At its lowest point, a narrow slot-shaped valley called the Challenger Deep. The ocean floor lies approximately 10,935 meters below sea level, nearly 11 kilometers straight down. The pressure at the bottom of the Challenger Deep is approximately 1,086 atmospheres, which means every square centimeter of surface there bears a weight of roughly 1,086 kilograms. Only 3 crewed missions have ever reached the Challenger Deep. The first was on January 23, 1960, when Swiss engineer Jacques Piccard and United States Navy Lieutenant Don Walsh descended in the Bathypelagic Trieste. They spent only about 20 minutes on the bottom before ascending, and during their brief stay, they reported seeing a flatfish-like creature on the seafloor, though this observation has been debated by scientists in the decades since. The second crewed descent came 52 years later in 2012, when filmmaker James Cameron piloted the Deep-Sea Challenger submersible to the bottom alone, spending several hours collecting samples and filming. The third came in 2019, when explorer Victor Vescovo reached the Challenger deep in the submersible limiting factor. So few have been, so much remains unseen. The Hadal zone, more than any other place on Earth, represents the true frontier of exploration, a place where the boundary between the known and the unknown is measured in fathoms of silent, crushing dark. But it is not only the trenches that hold the ocean's secrets. Some of the most astonishing discoveries of the 20th century came not from the deepest points, but from the spreading ridges where tectonic plates pull apart and new seafloor is born. In 1977, scientists aboard the deep-sea submersible Alvin, operated by the Woods Hole Oceanographic Institution, descended to a depth of roughly 2,500 meters along the Galapagos Rift in the eastern Pacific. What they found there transformed our understanding of life on Earth. Clustered around cracks in the volcanic rock, where superheated water rich in hydrogen sulfide and dissolved minerals gushed from the seafloor, were thriving ecosystems unlike anything previously known. Giant tube worms, some reaching over 2 meters in length, swayed in the current. Pale crabs and eyeless shrimp crowded around the vents. Thick mats of bacteria coated every surface. These were hydrothermal vents, and the ecosystems surrounding them did not depend on sunlight at all. Instead, they were powered by chemosynthesis, a process in which specialized bacteria convert chemical energy from hydrogen sulfide and other compounds into organic matter. This was revolutionary. Before this discovery, it was a foundational assumption in biology that nearly all life on Earth ultimately depended on photosynthesis, on sunlight. The hydrothermal vent communities shattered that assumption and opened an entirely new chapter in our understanding of where life can exist. Some scientists now propose that life on Earth may have originated at hydrothermal vents on the ancient seafloor billions of years ago, in conditions not unlike those we find at the vents today. This hypothesis, while not yet proven, is supported by multiple lines of evidence and remains one of the leading theories for the origin of life. And so these vents, these cracks in the ocean floor where the planet's inner heat bleeds into the cold water above, may be more than curiosities. They may be the cradle of everything. Let that thought drift over you now, warm and weightless, as the deep continues its slow, ancient exhale. There is another kind of oasis in the deep, quieter and stranger than the vents, and it begins with death. When a great whale dies in the open ocean, its body eventually sinks. A fully grown blue whale can weigh over 150 metric tons, and when that enormous mass settles on the abyssal floor, it creates what marine biologists call a whale fall. A whale fall is an event of extraordinary ecological significance. In the nutrient-poor darkness of the deep sea, a single whale carcass can sustain an entire community of organisms for decades. The process unfolds in stages. First come the mobile scavengers, hagfish and sleeper sharks, and amphipods, which can strip the soft tissue from the bones within months. Then come the opportunistic colonizers, polychaete worms and crustaceans, which feed on the remaining organic material and on the enriched sediment surrounding the skeleton. And finally, in what scientists call the sulfophilic stage, specialized bacteria colonize the whale's bones, breaking down the lipids stored within them and producing hydrogen sulfide as a byproduct. This creates conditions remarkably similar to those of hydrothermal. And indeed, some of the same species found in vents have been discovered living on whales. Current research suggests that whale forms may serve as stepping stones for deep sea species, allowing vent-seeking organisms to disperse across the vast distances of the abyssal plains by hopping from one whale carcass to the next. Before industrial whaling dramatically reduced great whale populations beginning in the 18th century, whale falls may have been far more common, perhaps one every 12 to 16 kilometers along the ocean floor in productive regions. The reduction in whale numbers may have disrupted these biological corridors in ways we are only beginning to understand, and so even in death, the whale gives. Its body becomes a world, its bones become a garden. And somewhere on the dark ocean floor, right now, at this very moment, creatures are feeding on the generosity of a fallen giant, living quietly in a cathedral of bone, unhurried, sustained, at peace. As we drift further into the deep tonight, let us consider what we know about the creatures that live in these extreme environments, and more importantly, what we do not. The deep ocean is the least explored biome on Earth, and new species are discovered with almost every expedition that descends below 1,000 meters. In the Hadal trenches, scientists have found snailfish living at depths exceeding 8,000 meters, making them among the deepest dwelling fish ever recorded. These fish are small, translucent, and seemingly fragile, yet they thrive under pressures that would crush a submarine. Their cells contain high concentrations of a molecule called trimethylamine N-oxide, or TMAO, which stabilizes their proteins against the distorting effects of extreme pressure. The deeper the fish lives, the higher its TMAO concentration tends to be, and scientists believe there may be a biochemical limit somewhere around approximately 8,200 to 8,400 meters, beyond which fish physiology simply cannot function. Below that, the trenches belong to the invertebrates, to amphipods, sea cucumbers, and foraminifera, single-celled organisms that build intricate shells from sediment particles. In the Mariana Trench, researchers have found giant amphipods, crustaceans related to the tiny sand fleas of the beach, measuring over 30 centimeters in length, a phenomenon known as deep-sea gigantism. Why some deep-sea creatures grow so large remains an open question. Some researchers suggest it may relate to the cold temperatures, which slow metabolism and allow longer growth periods. Others propose it may be linked to food scarcity, where larger body size confers an advantage in storing energy between infrequent meals. We do not yet know the answer for certain, and that uncertainty is, in its own way, a kind of gift. It means the deep still has stories to tell, stories that no one has heard, waiting in the dark like something precious held gently in the palm of an outstretched hand. Let the mystery hold you. There is comfort in not knowing everything. One of the most humbling aspects of the deep ocean is how much of it we have never seen at all. The technology required to explore these depths is extraordinarily specialized and expensive. Crude submersibles capable of reaching full ocean depth can cost tens of millions of dollars to build and operate. Remotely operated vehicles, or ROVs, connected to surface ships by long tethered cables are more common, but even they can only survey a tiny fraction of the seafloor during any given expedition. Autonomous underwater vehicles, or AUVs, can cover greater distances but lack the real-time decision-making and dexterity of crewed or remotely piloted craft. The most comprehensive effort to map the global ocean floor is the Seabed 2030 project, a collaborative initiative launched in 2017 by the Nippon Foundation and the General Bathymetric Chart of the Oceans, known as GBCO. Its goal is to produce a complete high-resolution map of the world's ocean floor by the year 2030. As of recent reports, roughly 25% of the ocean floor had been mapped to modern standards, a dramatic increase from the roughly 6% that had been mapped when the project began, but still leaving three-quarters of the seafloor unsurveyed completely. Much of what we currently know about the shape of the ocean floor comes not from direct sonar surveys, but from satellite altimetry, a technique that infers seafloor topography from subtle variations in the height of the sea surface caused by the gravitational influence of underwater mountains and trenches. This method provides a rough picture, but its resolution is limited to features larger than roughly 1 to 5 kilometers across. Anything smaller than that, a seamount the size of a city, a canyon the width of a river, remains invisible from space. And so the maps we have, as impressive as they are still sketches. The fine detail, the intimate topography of the ocean floor remains largely a matter of imagination. Somewhere beneath the waves tonight, there are features no human eye has ever seen, no instrument has ever measured, waiting dark, patient and slow. Beneath the sediment of the ocean floor, there is yet another world, one that challenges our very definition of life. In the 1990s and 2000s, scientists began drilling into the deep seabed and discovering microbial life buried in sediment layers hundreds of meters below the ocean floor. These organisms, mostly bacteria and archaea, live in conditions of extreme energy limitation. They metabolize so slowly that a single cell division, the most fundamental act of life, may occur only once every 100 years, or even once every several thousand years. To put that in perspective, the bacterium Escherichia coli, a common inhabitant of the human gut, can divide once every 20 minutes under favorable conditions. The microbes of the deep subsea floor exist on an entirely different timescale, one measured not in minutes or hours, but in centuries and millennia. Researchers estimate that the deep subsea floor biosphere may contain roughly 70% of all microbial cells on Earth, representing a staggering amount of biomass hidden beneath the ocean floor. Some of these organisms have been found in sediments estimated to be over 100 million years old, though whether the microbes themselves have survived that long or colonized the sediments more recently remains an active area of investigation. What is clear is that the deep subsea floor is not a dead place. It is alive in the slowest, quietest, most patient way imaginable. These organisms do not move. They barely metabolize. They exist in a state that some researchers have described as halfway between life and death, persisting on vanishingly small amounts of chemical energy extracted from the minerals and organic compounds trapped in the sediment around them. It is a form of existence so different from our own that it challenges us to reconsider what it means to be alive. Perhaps life does not require speed or growth or change. Perhaps, at its most essential, life is simply the refusal to stop. A persistence, a quiet, unbroken continuity, stretching through the dark, enduring, the way sleep endures through the longest night. The deep ocean also holds clues to our planet's past, preserved in the sediment and in the chemistry of the water itself. Ocean sediment cores, long cylinders of mud extracted from the seafloor by drilling ships, serve as archives of Earth's climate history. By analyzing the shells of foraminifera, those tiny single-celled organisms preserved in the sediment, scientists can determine the temperature and chemistry of the ocean at the time each layer was deposited. The ratio of two oxygen isotopes, oxygen-16 and oxygen-18, within these shells varies with temperature and ice volume, allowing researchers to reconstruct global climate conditions stretching back millions of years. The International Ocean Discovery Program and its predecessors, the Deep Sea Drilling Project and the Ocean Drilling Program, have collected sediment cores from oceans around the world since 1968. These cores have revealed the history of ice ages and warm periods, the opening and closing of ocean gateways, the evolution and extinction of marine species, and the timing of massive volcanic events. One of the most significant discoveries made through ocean drilling was the confirmation of the Chicxulub asteroid impact, the event that contributed to the mass extinction roughly 66 million years ago that ended the age of the non-avian dinosaurs. A thin layer of iridium-rich clay found in ocean sediment cores worldwide at the boundary between the Cretaceous and Paleogene periods provided key evidence for this impact hypothesis. The ocean floor, then, is not merely a landscape, it is a library. Every grain of sediment is a page, every layer a chapter, and the story they tell stretches back to times when the continents wore different shapes and the sky held a different chemistry. And tonight, as you rest upon a planet whose history is written in the quiet dark beneath the sea, in a language of shells and minerals and isotopes, patient and precise, waiting to be read. The ocean's influence on our world extends far beyond its depths. The deep ocean plays a critical role in regulating Earth's climate through a system known as the thermohaline circulation, sometimes called the global ocean conveyor belt. This vast, slow current is driven by differences in water temperature and salinity. In the high latitudes of the North Atlantic near Greenland and Iceland, cold, salty surface water becomes dense enough to sink to the ocean floor, beginning a journey that will carry it southward through the Atlantic, around the southern tip of Africa, into the Indian and Pacific Oceans, and eventually back again. A single parcel of water completing this full circuit may take roughly 1,000 years. The thermohaline circulation transports enormous quantities of heat around the planet. It carries warmth from the tropics toward the poles and draws cooler water back toward the equator, moderating temperatures on every continent. Without this circulation, northern Europe would be significantly colder than it is today. The deep ocean also acts as a vast reservoir for carbon dioxide. The oceans absorb roughly 25 to 30% of the carbon dioxide that human activities release into the atmosphere each year. Much of this carbon is transported to the deep ocean through a combination of physical mixing and biological processes collectively known as the biological carbon cycle, in which organisms at the surface incorporate carbon into their bodies and then transported to depth when they die and sink. This process has buffered the planet against even more severe atmospheric warming. But it comes at a cost. The absorption of carbon dioxide is making the oceans more acidic, a process known as ocean acidification. Since the beginning of the industrial era, the average pH of the ocean surface has decreased by approximately 0.1 units, which represents roughly a 26% increase in hydrogen ion concentration. The long-term consequences of this acidification for deep-sea ecosystems remain one of the most urgent and misunderstood questions in modern science. The deep ocean absorbs our excess, it carries our heat, it stores our carbon, and it asks, so far, for nothing in return. There is one more mystery of the deep that deserves our attention tonight, one that connects the ocean not only to the history of life on Earth, but to the possibility of life beyond it. In the outer solar system, several moons are now believed to harbor vast oceans of liquid water beneath their icy surfaces. Europa, a moon of Jupiter roughly the size of Earth's own moon, is thought to possess a global ocean beneath a shell of ice perhaps 10 to 30 kilometers thick. This ocean may contain more than twice the volume of all the water in Earth's oceans combined. Enceladus, a small moon of Saturn only about 500 kilometers in diameter, has been observed by NASA's Cassini spacecraft projecting plumes of water and ice particles from fractures near its south pole. Analysis of these plumes revealed the presence of salts, silica nanoparticles, and simple organic molecules, suggesting hydrothermal activity on the moon's ocean floor. The conditions there may bear a striking resemblance to the hydrothermal vents of Earth's deep ocean, the very environments that some scientists believe may have given rise to life on our own planet. And so, the deep ocean is not only a frontier of exploration on Earth, it is a model, a template, a rehearsal for the search for life elsewhere in the cosmos. When we study the chemosynthetic ecosystems of our own seafloor, we are, in a very real sense, preparing to understand what we might one day find beneath the ice of a distant moon. Every submersible descent to a hydrothermal vent is also quietly a rehearsal for one of the most profound questions our species has ever asked. Are we alone? The deep ocean whispers to us that life finds a way in darkness, in pressures, in cold, in the absence of light. And if it can do so here, on our own world, then perhaps somewhere out there, in an ocean we have never seen, beneath ice we have never touched, life is stirring in the dark. Let that possibility rest beside you tonight, warm as starlight, quiet as the deep. And so we arrive at the quiet center of this journey, the place where wonder and rest converge. We have traveled from the sunlit shallows through the twilight, where billions of creatures rise and fall each night in silent migration, past the midnight zone, where the giant squid drifts with its ancient watchful eyes, down through the abyss where nodules grow with the pace of deep time, and into the trenches where the earth itself bends and folds beneath the weight of the water above. We have touched the hydrothermal vents where life may have first stirred, the whale falls where death becomes a god, the deep subsea floor where microbes persist on timescales that dwarf all of human history. And through it all, one theme has held. The ocean is patient. It does not rush. It does not demand to be understood all at once. It reveals itself slowly, in fragments, in glimpses caught by the lights of submersibles and the patience of scientists who dedicate their lives to questions that may not be answered in their lifetimes. There is something deeply restful in that. In a world that often feels urgent and loud, the deep ocean reminds us that the most profound things unfold in silence, in darkness, over timescales that make our hurry seem almost complicated. The deep does not care about deadlines. It does not worry about tomorrow. It simply is vast and dark and full of life we have not yet lived, full of stories we have not yet heard. And you, lying here now, breathing slowly, are part of this same planet, this same system of water and stone and living things. The oxygen in your lungs was made in part by the ocean. The water in your body was once rain, was once river, was once sea. You are connected to the deep in ways that are older than memory, older than language, older than thought. Let the deep hold you now. Let its patience become your peace. Let its darkness become your rest. Consider for a moment the sheer volume of water that blankets this planet. The ocean holds approximately 1.335 billion cubic kilometers of water, a number so vast that it resists comprehension, a quantity that dwarfs every lake, every river, every glacier and aquifer combined into something almost negligible by comparison. And within that immensity, there are regions we have mapped with less detail than the surface of Mars. The seafloor, which covers roughly 71% of Earth's surface, has been mapped at high resolution across only a fraction of its entirety. As of recent estimates from the Nippon Foundation GEBCO Seabed 2030 project, approximately 25% of the ocean floor has been mapped to modern bathymetric standards, a figure that has grown significantly in recent years, but still leaves enormous stretches of terrain as unknown to us as the far side of a distant moon. What lies beneath those unmapped waters is not nothing. It is geology we have never described, ridges and valleys and plains that have never been named, ecosystems that may function according to rules we have not yet imagined. Every time a research vessel drags a sonar array across a previously unsurveyed patch of ocean floor, it tends to find something unexpected. A seamount that rises thousands of meters from the abyssal plain, a hydrothermal field venting minerals into the water column, a canyon system rivaling the grandeur of anything carved into continental rock. The mid-ocean ridges alone, that vast chain of underwater mountains stretching over 65,000 kilometers through every major ocean basin, represent the longest mountain range on Earth, and yet much of their fine detail remains uncharted. We know they exist. We know they are the birthplace of new oceanic crust, where tectonic plates spread apart and magma wells up to fill the gap. But the precise topography of their flanks, the locations where countless hydrothermal vents, the communities of life that cluster around those vents, these remain in many places matters of educated conjecture rather than confirmed observation. And yet, even in the places we have visited, the ocean guards its secrets with a patience that humbles every expedition. The Hadal zone, that collection of narrow trenches plunging below 6,000 meters, occupies less than 1% of the ocean floor by area. But it represents some of the most extreme environments on the planet. The Mariana Trench, the deepest known point in any ocean, descends to approximately 10,935 meters at its lowest surveyed point, a place called Challenger Deep. Only a handful of crewed missions have ever reached that depth. The first, in 1960, carried Swiss oceanographer Jacques Picard and United States Navy Lieutenant Don Walsh aboard the Trieste, a vessel that took nearly 5 hours to sink through the water column to the bottom. They stayed for roughly 20 minutes before the window cracked and they had to ascend. And still, in that brief visit, they reported seeing a flatfish-like creature resting on the sediment, though this observation has been debated by marine biologists in the decades since. What is not debated is that life does exist in these crushing depths. Expeditions using remotely operated vehicles and landers have documented amphipods, snailfish, sea cucumbers, and microbial communities thriving under pressures exceeding 1,000 times the atmospheric pressure at sea level. Some of these organisms possess proteins and cellular structures adapted to function under conditions that would destroy most surface life. Scientists believe these adaptations may have taken millions of years to evolve, shaped by the relentless, unchanging pressure and near-freezing temperatures of the deep trenches. And beyond the Mariana Trench, there are dozens of other Hadal trenches scattered across the Pacific, Atlantic, and Indian Oceans. The Tonga Trench, the Kermadec Trench, the Philippine Trench, the Puerto Rico Trench, many of which have been sampled only sparingly, or not at all, by modern scientific instruments. Each one is a world unto itself, isolated by depth and distance, harboring communities of life that may differ significantly from trench to trench. Somewhere in that darkness, beyond the reach of sunlight, beyond even the faintest trace of the photons that warm our skin in summer afternoons, there exists a form of life that rewrites the very definition of what it means to be alive. Chemosynthetic ecosystems, first discovered in 1977 near the Galapagos Rift by scientists aboard the research submersible Alvin, revealed that life on Earth does not require the sun. Around hydrothermal vents, where superheated water rich in hydrogen sulfide and other chemicals billows from cracks in the seafloor at temperatures that can exceed 350 degrees Celsius, bacteria harvest chemical energy rather than light energy to produce organic matter. These microbes form the base of an entire food web, giant tube worms, some growing over 1.5 meters in length, clams, mussels, shrimp, and crabs, all sustained not by photosynthesis, but by the chemical breath of the Earth itself. Current evidence suggests that there may be thousands of active hydrothermal vent fields scattered along the mid-ocean ridges and in backmark basins around the world, yet only a few hundred have been directly observed by human instruments. Each newly discovered vent field has the potential to harbour species found nowhere else, organisms uniquely adapted to the precise chemistry and temperature of their particular. Some researchers propose that life on Earth may have originated in environments similar to these, warm, mineral-rich, sheltered from the ultraviolet radiation that bathed the early planet's surface. This remains one of science's great open questions, but the idea carries a quiet, profound implication. If life can begin and flourish in total darkness, sustained by nothing more than heat and chemistry, then perhaps the deep oceans of other worlds, the subsurface seas of Europa, the hidden waters that may lie beneath the ice of Enceladus, could harbour life that was worthy. The ocean, it seems, does not merely contain mysteries. It offers us a lens through which to imagine the possibilities far beyond this world. Let us rest here for a moment, suspended in the quiet awareness that the ocean is not simply a body of water, but a living archive, a record of often in salt and sediment and the slow drift of continents. The abyssal plains, those vast flat expanses that cover roughly half of the ocean floor, are blanketed in sediment that accumulates at an almost unimaginably slow rate, in some places only a few centimeters every 1,000 years. Within those layers lie the shells of microscopic organisms called foraminifera, tiny calcium carbonate structures that have been drifting to the seafloor for hundreds of millions of years. By studying the chemical composition of these shells, particularly the ratios of oxygen isotopes locked within them, scientists can reconstruct the temperature of ancient oceans, the volume of ice that once covered the continents, and the rhythms of climate change stretching back tens of millions of years. These sediment cores are among the most important records of Earth's climate history that we possess, and yet vast regions of the abyssal plains have never been recorded at all. There are stories buried beneath us, written in a language of chemistry and geology that we have not yet learned to read in full. And the ocean floor holds more than climate records. In certain regions, scattered across the abyssal plains like quiet sentinels, lie polymetallic nodules, potato-sized concretions of manganese, nickel, cobalt, and other metals that grow by precipitating dissolved minerals from the seawater above them at a rate of roughly 5 to 20 millimeters per million years. Some of these nodules began forming tens of millions of years ago. They sit on the sediment in silence, accumulating their layers atom by atom, unbothered by the passage of epochs. They are among the slowest growing objects on Earth, and their very existence is a meditation of patience, on the kind of time the deep ocean inhabits so naturally, and that we, in our waking lives, so rarely allow ourselves to feel. Consider for a moment the Hadal zone, that realm of the ocean named after Hades, the ancient Greek god of the underworld. It begins at roughly 6,000 meters below the surface and descends into the narrow, plunging trenches that scar the ocean floor where tectonic plates converge. These trenches are not wide basins, but rather long, tapering wounds in the Earth's crust, some stretching for hundreds of kilometers while remaining only a few kilometers across. The deepest of them all, the Mariana Trench in the western Pacific, reaches a confirmed depth of approximately 10,935 meters at its lowest surveyed point, known as the Challenge Deep. Fewer than 2 dozen people have ever descended. And yet the Hadal zone is not a single place. It is a scattered archipelago of extreme environments, comprising perhaps 33 trenches and troughs distributed across all the world's major oceans. Together, they account for roughly 45% of the ocean's total depth range, and yet they represent less than a quarter of 1% of the total seafloor by area. We have sampled only a handful of them with any scientific rigor. The pressures at these depths are staggering, exceeding 1,000 times the atmospheric pressure at sea level, a force so immense that it would crush most human-made instruments. And still, life persists there. In the 1950s and 60s, early expeditions using deep trawling nets pulled strange, translucent amphipods and delicate sea cucumbers from the dark depths. More recently, autonomous lander vehicles equipped with cameras and bait traps have revealed thriving communities of scavenging crustaceans, snailfish gliding through absolute darkness, and microbial mats coating the sediment with quiet, ancient metabolism. Scientists believe that many Hadal species are endemic, meaning they exist in only one trench and nowhere else on Earth, isolated by the abyssal plains that separate one trench from another, like deserts separating oases. Each trench, then, is its own island of life, shaped by its own particular pressures, temperatures, and chemistry, and most of them remain entirely unexplored. And then there are the sounds, the vast, echoing acoustic landscape of the deep ocean, a world of noise and silence that we are only beginning to decipher. Water carries sound far more efficiently than air, roughly 4.5 times faster, and in the ocean there exists a natural channel, a layer typically found between about 600 and 1200 meters deep, where temperature, pressure, and salinity combine to create a zone of minimum sound velocity. This layer is known as the SOFAR channel, an acronym for sound fixing and ranging, and it acts as a kind of acoustic waveguide. Sounds that enter this channel can travel for thousands of kilometers without significant loss of energy, bending back and forth within the layer like light trapped inside a fiber optic cable. It was through this channel that scientists in the 1960s and 70s began detecting strange, powerful, low-frequency sounds emanating from the deep ocean, signals that had no obvious origin. Some of these sounds have since been explained. The famous bloop, recorded in 1997 by hydrophones operated by the United States National Oceanic and Atmospheric Administration, was once a source of fascination and speculation, but subsequent analysis strongly suggests it was produced by the cracking and calving of a large Antarctic iceberg. Other sounds have been attributed to underwater volcanic activity, to the shifting of tectonic plates, or to the resonant vibrations of ice shelves. And yet, not all oceanic sounds have been so neatly resolved. Some low-frequency signals recorded over the decades remain ambiguous, their sources uncertain. More intriguingly, we know that many deep-sea species produce sounds, clicks, pulses, low moans, that we have barely captured. Whale species such as the blue whale and the fin whale produce calls that can travel across entire ocean basins through the SOFAR channel, songs that pulse through the darkness at frequencies as low as 14 to 17 hertz, near the threshold of human hearing. Somewhere beneath the waves right now, as you listen to these words, the ocean is singing to itself in voices we have not yet learned to name. Beneath the sediment of the ocean floor, there is yet another world, one that challenges our very definition of life. Drilling projects, most notably those conducted by the Integrated Ocean Drilling Program and its successor, the International Ocean Discovery Program, have extracted cores of sediment and rock from hundreds of meters below the seafloor. Within these ancient layers, scientists have found microbial cells, extraordinarily small, extraordinarily slow, undeniably alive. These organisms belong to domains of life that include both bacteria and archaea, and some of them subsist on vanishingly small amounts of energy, metabolizing at rates so slow that a single cell division may take decades, perhaps even centuries. Current evidence suggests that the total biomass of microbial life within subsea floor sediments is immense, potentially comprising a significant fraction of all microbial life on Earth, though estimates have been revised downward from earlier projections. Some researchers have proposed that these deep biosphere communities may have persisted in relative isolation for millions of years, slowly consuming buried organic matter, or extracting energy from chemical reactions between water and rock in a process process known as serpentinization. It is a form of existence so profoundly different from our own that it invites us to reconsider what living truly means. These organisms do not swim, they do not hunt, they do not reproduce with any urgency we would recognize. They simply endure, locked within their mineral chambers, ticking along on timescales that dwarf the entire span of human civilization. And we have sampled only the thinnest fraction of this subsea floor realm. The ocean crust itself, the basaltic rock beneath the sediment, extends for kilometers in some places. And there are tantalizing signs that microbial life may penetrate even there, dwelling in the hairline fractures and porous spaces of ancient volcanoes. If this is confirmed, then the true boundary of life on Earth extends far deeper than we have yet imagined, down into the slow, warm darkness of the planet itself. Across millions of years, the ocean has also been a keeper of objects, a silent archivist of everything that has ever sunk beneath its surface and come to rest on the bottom. We tend to think of the seafloor as barren, but it is in fact a vast repository of history, both geological and human. There are an estimated 3 million or more shipwrecks resting on the ocean floor worldwide, according to figures cited by the United Nations Educational, Scientific and Cultural Organization. And the great majority of them have never been located, surveyed, or even identified. Some are ancient, Phoenician trading vessels, Roman galleys, Chinese junks from the era of the Song dynasty, their timbers long since consumed by wood-boring organisms, leaving only faint impressions in the sediment and scatterings of ceramic, metal, and stone. Others are more recent, warships and merchant vessels from the great conflicts of the 20th century, their hulls slowly dissolving into the salt water, their cargoes of personal belongings and wartime materials settling into the ooze. Each wreck is a frozen moment, a small capsule of human intention interrupted by the sea. And beyond human artifacts, the ocean floor preserves geological records of extraordinary value. Layers of sediment accumulate at rates of only a few centimeters per 1,000 years in the deep ocean. Within those layers are the shells of foraminiferae, microscopic organisms whose calcium carbonate tests record the temperature and chemistry of the water in which they live. By analyzing oxygen isotope ratios in these shells, scientists have reconstructed detailed records of Earth's climate stretching back tens of millions of years, revealing the rhythmic advance and retreat of ice ages, the slow drift of continents, and sudden warming events whose echoes may inform our understanding of the present. The ocean remembers what the land forgets. It holds the long, patient record of this planet's story, written in sediment and shell and silence, waiting in the dark for someone to read it. And yet the ocean holds something perhaps more profound than any single artifact or fossil. It holds memory itself, written into the chemistry of its waters, encoded in layers of sediment that have been settling grain by grain for hundreds of millions of years. Oceanographers call these layers the sedimentary record, and they form one of the most complete archives of Earth's climate history that we possess. Each centimeter of deep-sea mud may represent thousands of years of accumulated time. The shells of foraminifera, tiny single-celled organisms no larger than a grain of sand, drifting down through the water column after death and coming to rest on the abyssal floor. The ratio of oxygen isotopes locked within those microscopic shells tells scientists about the temperature of the water in which the creature lived. And from that, they can reconstruct global climate patterns stretching back tens of millions of years. It was through such analysis that researchers confirmed the rhythmic cycles of ice ages, driven in part by slow variations in Earth's orbit known as Milankovitch cycles, named after the Serbian mathematician Milutin Milankovic, who proposed the theory in the early 20th century. And so the ocean floor is not merely a resting place. It is a library, vast and unburdened, where the slow handwriting of planetary change is preserved in a language of calcium carbonate and silica, but much of this library remains unread. We have drilled core samples from only a fraction of the ocean floor, and there are basins, trenches and abyssal plains where no instrument has yet touched the sediments. Somewhere beneath the Southern Ocean, or in the unexplored reaches of the Central Pacific, there may be records of climate events we have not yet imagined. Sudden warmings, ancient storms, volcanic winters that reshaped the trajectory of life on Earth. The ocean remembers what the continents have long forgotten, and it waits in its patient darkness for someone to ask the right questions. Consider for a moment the creatures that remain undiscovered, the animals, the microorganisms, the entire ecosystems that exist beyond the reach of human observation. Current estimates suggest that somewhere between 1 and 2/3 of all marine species have yet to be formally described by science. The Census of Marine Life, a decade-long international project completed in 2010 that involved thousands of researchers from more than 80 countries, catalogued approximately 250,000 known marine species and estimated that at least 750,000 more await discovery. And that estimate, many biologists suspect, may itself be conservative, particularly when it comes to the smallest forms of life, the bacteria, the archaea, the viruses that inhabit every drop of seawater and every gram of ocean sediment. In the Hadal zone, the narrow trenches that plunge below 6,000 meters, conditions are so extreme and so isolated that each trench may harbor species found nowhere else on Earth, shaped by millions of years of evolution in total darkness under crushing pressure. In 2012, filmmaker James Cameron descended to the bottom of the Mariana Trench in the submersible Deep Sea Challenger, reaching a depth of approximately 10,900 meters. And even in that brief visit to the deepest point on the planet, instruments recorded microbial life thriving in the sediment. Life, it seems, is more persistent than we ever imagined, more willing to inhabit the margins, more creative in its adaptations than any single theory could predict. There are amphipods in the trenches that have evolved unique proteins to protect their cells from the immense hydrostatic pressure. There are fish at abyssal depths with bones so thin that they are nearly transparent, their bodies little more than water held in delicate form. And for every species we have named, there are perhaps dozens more drifting through that darkness, unobserved, uncatalogued, living out entire evolutionary histories without ever being witnessed by a human eye. The ocean is still now, not truly still, of course, for it is never truly still, but still in the way that matters tonight. The currents move, the creatures drift. The marine snow continues its long, gentle fall through miles of dark water, and somewhere a whale's bones are feeding a garden no one has ever seen. You do not need to think about any of this anymore. You do not need to hold these facts or remember these numbers. Let them dissolve the way light dissolves in deep water, softly, gradually. until only the feeling remains. You are safe. You are warm. You are held by the same gravity that holds the ocean in its basin, the same slow turning of the earth that moves the tides. Let your breathing slow to match the rhythm of the deep. Let your thoughts sink gently like sediment, settling on a floor you do not need to see. The deep is patient. The deep will be there tomorrow, and the day after, and the day after that. For now, there is only this: darkness, warmth, the quiet sound of your own breathing. Rest now. The ocean rests too. If this journey brought you a moment of peace, you might consider subscribing so that the next time you need the deep to carry you to sleep, it will be here, waiting. Leave a thought in the comments if you like. Tell us what part of the ocean you would most like to see. And next time, we will explore the silence between the stars, the vast, empty spaces where light itself grows tired.